flashlights. So here we have two main goals. The first one is to measure water ice concentration on the lunar South Pole with a minimum resolution of 0.5 weight percentage of water ice within the regolith. And the second one is to map water ice distribution with a minimum resolution of 1 to 10 kilometers. So that's a spatial resolution for the minimum success criteria. And for the full success criteria, sorry, and for the minimum success criteria, that's 10 kilometers. And some LIDAR instruments actually also have already continued strong indication of water ice present within the PSR using reflectance measurements at 1 micron, even if these instruments were not designed for that purpose. For example, LOLA, which was an altimeter. So we know that these techniques works actually, but in order to precisely quantify water ice within the PSR, and in order to be able to discriminate it from the other lunar polar vortices, we need to expand that technique using more than one wavelength. And so that's why we have designed what we call shortwave infrared multiband laser reflectometer. So here actually we have the picture of the CubeSat. That's a 6-unit CubeSat. So it's pretty small. It has almost the size of a shoebox. And you have 2 units of volume here allocated to an instrument. So you have a zoom of the instrument here. Now remember that we are primarily interested in mapping water ice within the PSR, right? By definition, there is no sunlight. So we need to bring our own source. So that's why we'll use several lasers, in our case emitting at different wavelengths between 1 and 2 microns. So how does that work? So you have the CubeSat here, the instrument. You have several lasers emitting sequentially different pulses between 1 and 2 and 6 millisecond pulses at different wavelengths. So the wavelength here that we are using are these ones. So 2 of them just correspond to peaks absorption for water ice, and the 2 others are just nearby continuum. And these lasers emit optical output power between 14 and 73 watts, depending on the wavelength. So we'll fire with this laser the moon surface, and a part of the reflected light here will be just a part of the light, here will be just reflected towards the receiver aperture, and the receiver will just measure that reflected line, and then we'll be able to derive the reflectance of the moon surface at these 4 different wavelengths, and then derive the reflectance band ratio and measure the water ice within the illuminated spot here. So an important thing also here is that you can see that after each laser firing sequence, you have a pause here of 1 to 6 milliseconds with all the lasers off. And during that time, we'll just measure the background, which is actually the thermal emission of the instrument, but also the document of the detector and the solar stray light that will detect with the receiver from its inside and outside the field of the instrument. And then we'll just subtract that background to all the measurements to derive the reflectance and different wavelengths. So first, we'll speak about the transmitter, which is just basically the laser. So in our case, we'll use several high-power diode lasers that's based on customized epitaxy procured from DLAS Incorporation. We'll pump this laser at 45 amps. So as I already say, that should correspond to optical output power between 14 and 70 watts. Here are the requirements for the divergence and the co-alignment. And the main requirement here, not the main requirement, but the main constraint is a thermal constraint. Actually, we will be able to output optical power using this laser during a maximum time of 2.5 to 3 minutes for continuous operation. And how we'll do these lasers? Using a phase change material. So that's a picture of a PCM here. That's not exactly the one that we'll use. It's just an example. That's actually the PCM of another CubeSat mission. And this thing is just based on some paraffin mixed with carbon fiber inside. I would like to point it out so that it's not a problem to only being able to operate this laser during such a small time. because we work with highly elliptical orbits. The period of these orbits will be between 5 and 7 days, and during that time, we'll only be above the region of interest on the lunar south pole during 6 minutes. And 3 minutes over 6 minutes, that's enough in our case to target the PSR and to measure weather ice inside the PSR. So this laser will be pumped using this electronics, and this electronics, the power will come from some batteries actually. So that's the picture of the real electronics that we are currently testing. Again, there is a big thermal constraint here. The maximum continuous operational time will be between 2 and 3 minutes. That's a good point because that's more or less the same thermal constraint than for the lasers. To give you an idea, the thermal dissipation of these two barrels is more or less equal to 60 watts. And more or less half of that power provided from these four different MOSFET switches. That's not shown here in the picture, but actually they will be thermally strapped to the CubeSat structure to passively cool them, and that's how we were able to optimize that operational time. So here is another subsystem, so the receiver. Sorry about that. This receiver is still being manufactured, so I don't have a picture of the real hardware. So that's just the CAD model of the receiver. First thing is that we only have one unit of volume allocated to the receiver. So this thing has to be as simple as possible. And our idea here was designed a very simple optical design just based on an off-axis aluminum parabolic mirror, which will focus the incoming light here onto a single pixel detector located here at the focal position. So what you can see here is that this thin black layer is just the chip where you have the detector. The detector is glued on this cold finger, which is thermally strapped to a cryoradiator to passively cool the detector during the mission. You will have also a heater glued on this cryoradiator, and using a PID regulator, we'll regulate the temperature of the detector during operation to minus 65 degrees Celsius. Everything is, not everything, but more or less everything is built with aluminium to get a more or less athermal system or close to it. The detector is a lithium gallium arsenide detector with extended wavelength. So in our case, that's a 2.4 micron wavelength. And this thing also, the optical design was optimized for stray light. So here what you can see is just a picture of the CubeSat. You are just above the PSR. That's a representation here of the field of view of the receiver. But you can see that you have some surrounding solar light here, and a portion of it can still be reflected toward the instrument from outside the field of view. And because of some scattering process here within this box, some of that light can still reach the detector active surface area. So what we have done is that we have designed some vanes and baffles, so you can see a part of it here and here, to minimize the detection efficiency of this stray light from outside the field of view, using our model that uses actually the predicted orbits that we'll have, the exact lunar topology, and also the illumination of the moon. So that's here a representation of the field of view of the receiver. So basically that's the PST, the point source transmitted function, and that corresponds to the fraction of the photon at the receiver aperture here that will reach the detector active surface area as a function of the incident angle. So in our case, using a 2 mm diameter detector and a focal length of 70 mm for that mirror, we are about to get a uniform field of view of 20 millirad. So that's the region here inside this black circle. And if you put that black circle onto the beam divergence profile, like here, you can see that you can fully cover this divergence profile to maximize the number of photons that you will be able to detect, with some margin around here to accommodate the pointing instability budget. because you can basically have some misalignment during the mission because of some thermal gradients inside the structure of the instrument. So here is another subsystem. So we have already spoken about the laser package, the electronics that will be used to power that laser, as well as the batteries, the receiver here with the gray radiator. And here we have the electronics that will be used not only, that's not only for that, but that will also be used to measure the output current of that detector. So here you have the electromagnetic shield, and inside you have this board. So that's the real board that we'll use, but that's not populated yet by the components. And there was also a big challenge behind the system engineering of that part. So actually, because we use only COTS component, we have to optimize everything to minimize as much as we can the SLR of the instrument. But as you may know, if we are using a TIA, which is our case, so that's a 20 impedance amplifier, the gain bandwidth product is a constant. So if you want to increase the signal to noise ratio, you need to increase the gain. But in that case, we need to decrease the bandwidth. And if you decrease the bandwidth, you need to increase a little bit the pulse width to not being constantly in the transient regime. That's a problem. You cannot increase that pulse width too much, because otherwise, remember that you will only measure the background after one laser firing sequence. So here we assume that the background is more or less stable during that sequence, and if you increase too much the pulse width, maybe the background will fluctuate too much, and that will introduce systematic errors when you will subtract the background to each of the measurements. So what we did is that we have a model, a MATLAB model, that is simulating everything, so the predicted orbits, the noise of all the electronics, the PST of the receiver, the beam divergence profile, and so on. And we've said in our model many different design of that board, so many different bandwidth, gain, and related noise. And we picked up just the one that for which we optimized the science returns, and so that was this one. So a pretty small bandwidth, a current range between 0 and 10 nanoamps, and with an error noise of 8 picoamps. So here is the main output of this MATLAB model. So what you can see here is the reflectance signal to noise ratio for all the different wavelengths as a function of the operational time for the 11 orbits that we'll have. So you have some fluctuation as a function of time. It's just because the altitude is changing, and for some of these regions, we can see that the SLR drops to 0. Basically, that corresponds to region where you have a bright spot, so that will basically saturate the electronics, and so that's why the SLR drop to 0. Even if you optimize the design, not optimize, but even if you have a design for the electronics that allows you to have an infinite current range, for these very bright spots, you won't be able to get any good measurements, because only the shot noise related to that background will be too high to just kill your science result after the background subtraction. That's the second output of our model, and that's basically a very good representation, very good summary of the performance. So how to read that? Let's take an example. For example, from that point, you can see here that you can discriminate between 0% and 1% of water rays within the regolith at 2 sigma confidence level, and that's in yellow here. That will be for more or less 10% of the covered area during that mission. Very important thing here, we didn't include the uncertainty related to the calibration of the instrument. So in this thing, for the one, there is only the noise related to all the subsystem of the instrument. The reason why is that we are still optimizing our calibration plan to minimize as much as we can this uncertainty. So basically, that's what you would be able to do with the instrument if you base if you are using basically the relative difference between reflectance band ratio from one spot to the moon to the other spot to derive the polarized content. So for the conclusion, I have presented you the design of a very small form factor, a multi-band short infrared reflectometer that will be used to map and quantify water ice on the lunar south pole. The challenge in the system engineering part was actually challenging because this thing is so small that all the subsystems are coupled each together, for example, thermally, and you have to optimize everything to maximize the signal-to-noise ratio and operational time for each of the subsystems. The next step, of course, that will be to manufacture the rest of the flight modules, calculate, characterize everything, and then integrate everything to the CubeSat. And the last thing I want to say is that why this instrument is innovative, because that's a pretty, I mean, the design of this instrument is pretty simple, but actually that will be one of the first instruments on board the CubeSat to perform science measurement beyond the low Earth orbit. And that will be also the first planetary mission to measure reflectance from orbit using active sources. So that's why. So thank you very much for your attention. And finally, I just would like to emphasize that I'm almost at the end of my postdoc appointment, and I'm currently searching for an exciting new challenge. So if you are interested, feel free to contact me, and we can also speak after that. Thank you.